My last marker pass it? No, I got to go to the next one. Did this pass it? Yes. So my next one is from W3. So that's all I do is I initialize it, and then I just count up for however many samples that I need. I go and I grab the next wagon wheel chunk, and I see where on the CDF that it lands. And then I just return that set. It looks more complicated than it is, and it's a way of doing that sampling in linear time. That's sort of how to do sampling efficiently. The other thing is, how often do you have to resample? Well, in the algorithm that I showed you, we resample all the time, and that's so that we have a whole bunch of samples that are about uniform weight and we spread them out. If I don't have too many samples that have very large weights, maybe I don't have to resample. Maybe I can just reuse the weights, the same samples over again. Right? I still have to apply the deterministic part, and I have to apply the expansion part, but I don't have to do that resampling. And you can do that by just saying, let me take a look at sort of the variation in the weights. I want them as uniform as possible, and as long as they have a certain amount of uniformity to them, I won't resample. So that reduces the number of times you do resampling. A second problem is, what if P of z given x, what if your likelihood is incredibly peaked? Remember, you multiply the likelihood times the weights of the samples. If it's incredibly peaked, that means that P of z given x is 0 almost everywhere else. That's not very helpful, because what that means is you've wiped out all of your possible predictions. In general, you want to allow for noise in your P of z given x. Don't be so systematic about it. And you also might want to be better at sort of how you do your proposals to begin with, right? So you want to make sure that your particle filter sort of spreads out the points to begin with. And one way of doing that, actually, is if you think of a sample, each sample you can think of as having its own little mini Kalman filter. So you can think of it as having a Gaussian that sort of spreads itself out and goes forward. In general, you're much better off overestimating noise and let your measurements sort of narrow you down than underestimating noise and have your measurements think that they're much more accurate than they are, or I should say much more constraining than they are. Another issue is recovery from failure. Suppose an object really did disappear and reappear. If I have no particles there, I don't have any way of tracking it ever. So a standard thing to do is each iteration you randomly put out some particles everywhere, or sort of uniformly distributed. Because if my measurements suddenly have moved over here, there'll be some particles over there, and eventually that will be the distribution that will be tracked. So those three issues of sort of making sure you're smart and efficient about your resampling, not letting your system think that measurements are too precise, and making sure you have enough noise so that you don't kill off samples too quickly, and this idea of having some random samples distributed in a useful way so you can track things if things change very unexpectedly. All these things are necessary to make particle filtering work. That ends the robot vision part of particle filtering. Now, if you remember, we introduced all of this stuff in order to be able to do tracking. Okay, we started with Kalman filter tracking, then we did particle filter. So in our next lesson, what we're going to do is we're going to go back to doing tracking, and we'll use some simple particle filter technique for doing some visual tracking. All right, welcome back to computer vision. Today what we're going to do is we're going to finish up particle filtering, and we're going to sort of do particle filtering for real. We've mostly discussed it from an algorithmic perspective and sort of how it maintains a density estimate. And we even looked at some robot vision examples last time, localization through the Smithsonian and other things. And this time we'll talk a little bit about real vision and how you might do it. So if you remember this Bayesian filter framework, we had to have sort of 4 different elements, right? We needed a prior, which nobody ever talks about. It's kind of the black sheep of the family. A dynamical model, or an action model, that says how we think things change from moment to moment based upon where they were and the inputs that are provided. A sensor model, the likelihood of a measurement given state. And then we have this stream of observations, and the question is what to do with them. To do real tracking, we have to specify these things. In particular, we've got state and state dynamics, and we've got a sensor model. So in the math, it's easy. We just write X, and we say X is the state. But the state of what? Montana, with Missouri, you know what? No. is state of the object. Everybody says, oh, it's the state of the object. Well, what does that mean? Obviously some representation of the object, its position, its velocity, maybe something about whether it's happy or sad. And that sounds like a joke, but actually, if you can think about tracking the state of the object, there's no requirement that the state be a purely physical thing. It's anything that can have an influence on a sensor measurement that you want to know. Speaking of sensor measurements, or speaking of Z, that's the measurement. But the measurement of what? What measurement are you going to use, and how does the measurement relate to the state? So if we're going to do real tracking, we have to know these things. And finally, where do you get your dynamics from? Do you go to the dynamics shelf at Home Depot and say, I need some dynamics, please? Where are you going to get these for computer vision? The discussion we're going to use today comes a bit from this paper, and the idea of using particles and sample-based representations of densities, that wasn't new. That was known in a variety of mathematics and in other engineering fields. But this is the paper that really brought it to computer vision. We showed this picture already, right? This is the picture of the tracking of Andrew Blake's daughter. And the first question is, what is this state? All right? And the state, or the object that was to be tracked, was a hand-initialized contour of the head. On the left here, you see a bunch of contours, okay? In fact, there's even one that's up here, all right? Those contours are the contours represented by each or many of the particles, the top particles, right? And so, for example, you can actually talk about the mean state as being the sort of average of the particles. But that doesn't really tell you what it is. What do you mean, the state of a contour? Well, in fact, what they did is they drew a contour and they said, because that's not a parameter, that's a shape, and they said, let's represent the state of that contour by an affine deformation, okay? Remember affine? Affine is, it's a three-point to three-point mapping, takes how many parameters? It's 6 parameters, okay? Translation, rotation, scale, and shear, depending upon how you count those. I mean, it's 6, and you can sort of divide them up any way. So the idea is that each particle represents a 6-dimensional vector. So by the way, that means our particles are living in a 6-dimensional space. And the bigger the number of dimensions, the more particles you need to sort of fill up that space. In fact, it doesn't grow so nicely, does it, right? I mean, if I go from 2 dimensions to 3 dimensions, right, if I had 100 particles before, if I wanted to have the same density, I would now need 1,000 particles, right? It grows exponentially in terms of the number of dimensions. So for affine, we're going to need 6. And as I said, each of the particles represents that. Here, by the way, is one of the videos, and one of the questions you might ask is, well, where do you get the dynamics?
Where do you get the dynamics?
Well, there are a couple of things you can do. The easiest thing to do is to cheat, all right? So the reason we're using dynamics here is that the girl is jumping up and down in front of a cluttered background. So to keep track of where her head is kind of a difficult tracking problem. That's why we're doing all this work to begin with. That's why we're using particles. But when would tracking be easy? How about if she was jumping around in front of a green screen or a white background, okay? Or in fact, even easier, suppose you put her in a totally black turtleneck sweater and you put her in front of a black screen, kind of like that thing. By the way, Megan doesn't let me wear black shirts because I'll disappear. But the point of my disappearing is all you would see would be my floating head, which would be kind of creepy. But it would be very easy tracking. So you could have somebody jump around with their floating head, track it very easily, and measure the dynamics. So one way of getting dynamics is to sort of cheat and get it from an easier system. And I think for a bunch of the stuff they did in condensation, that's what they did. They had an easier problem. Something else they did was they tracked the state of the hand. So what do you mean the state of the hand? That's actually, I encourage you to read the paper. They did a couple of really cool things. First of all, you have translation. Okay, well, how many degrees of freedom in translation? Well, we're doing it in 2 dimensions, so there's 2 degrees of freedom. They had a rotation, okay, which is 1 degree of freedom. But the other thing they added to that was the shape of the hand. And you might ask, well, how did they encode the shape of the hand? Don't bother, Megan. Well, actually, what they did was they took a whole bunch of images of contours, and then they did a form of principal components analysis. Now, you may not know what that is, but the good news is you will. Very soon, we're going to do principal component analysis when we talk about recognition. The thing that matters is that it has a low-dimensional representation of a certain variation. And what they did is they extracted out, essentially, instead of keeping rotations separately, they took 10 degrees of freedom that represented the shape of the hand, including rotation. So you had 2 for translation and 10 for the rotation and shape. So that's a 12 degree of freedom space. So that's even more difficult to do the tracking with particles, because you have to have a lot of particles in order to do this. Okay, that's about the state. What about the measurement? Okay, what about Z? All right, here's another picture taken from that paper. And what they did was, in fact, if I go back to the hand thing, you'll see that the hand, what they want to do is track this contour. All right, and I'll draw it on the hand part. Well, if you've got the right state, then you would expect to have an edge in the image at the edge of where the state says the fingers are. That is, there's some relationship between the edges of the fingers in your state and the edges that you would see in your picture. And in fact, that's what they do. Okay, what they do is, and there's more derivation, basically they come up with a probability distribution that says that the probability of getting a particular measurement given the state, and remember the state tells me where the fingers are, is essentially an exponential, so like a Gaussian, that's proportional to the square of the distance to the nearest strong edge. So that was the original condensation paper. Like I said, it was in '98. There have been many versions subsequent, things that have to do with importance sampling that look at the particles and stuff. Here's another example of doing head tracking, 2002. And you can see it's a little hard right there, tracking the head there. Okay. There's an interesting example right here. You see the head here is fully visible, but then it goes behind the cabinet. In fact, the only part of the head that's visible I just outlined. In fact, only the top half is visible there. So the question is, how did they move through occlusion? Okay, because part of the head is missing. Well, maybe they used velocity in their state, or maybe they didn't. What do you think? You think they did, or you think they didn't? Personally, I would have thought they did, because, I mean, I know all about Kalman filtering. I know if you track velocity, it's really easy. But then, if I think about particle filters, I'd say I probably didn't need to track velocity for the following reason. It's not the case that it has to be a great example of a head contour. It has to be the case that the example of the head contour that's here is a better example than if I put the head somewhere else. And in fact, indeed, this paper, they tracked the head through the partial occlusion without velocity. Now, would it have worked if the head was totally occluded behind the cabinet? No, because then the thing would just stay there. In fact, they call it a velocity zero model. The particles just stay where they are and they just diffuse out from the uncertainty. And so if you showed up on the other side of the cabinet, you'd be out of the frame of view altogether. Yes, Megan, I'm back. Okay. Whereas if you did velocity, you would follow me. Follow me. There you go. Follow. Very, very good. So now you get the point. You can do interesting things with states. So here we have the head contour. Another kind of model is, suppose you've got some way of detecting colored blobs that represent, say, hands and head. Now your state might be the XY location of the hands and head, and your measurement might be where you think the colored blobs are, and your sensor model might be how well the predicted blobs match the color. You can use sort of any model you want as long as you can have a state and you can talk about how that state expresses itself. In fact, here's an even better model. Suppose you want to track some region of a distribution of colors, right? So like maybe this region here, or this region here where you can see the ellipse. So that kind of gives away that the region that we're gonna be tracking here. What would be a good model or state for tracking that? Okay. Well, clearly, you want the location, because after all, I want to know where the thing is, all right? And if I've defined a region, I want to know sort of how that region is changing, maybe a little bit in orientation or size. But just to tell me the position and the size, that's not enough. I need something about the appearance. In this particular method, and we're going to talk a lot more about this next time, what they tracked is really cool. They tracked the distribution of colors, right? So if I look over, let's say, I won't do that region. I'm going to do this region over here, right? There's some white pixels. There are some